Good evening, friends. Today we shall be discussing about the eddy current losses in a solid conductor. So we have chosen a conductor of copper, and its cross section is given by H into B, and we have chosen an element dx at a distance x from the base of the conductor. The conductor is placed in a slot of width ws. The sectional view is given by this diagram. It is length ls, and this element when viewed from this along this section looks like this, and the resistance of this element is rho L by A, rho ls by B dx, B into dx. Now what is d phi x? D phi x is the flux linked by this element or this section. Simply mmf by reluctance. mmf is given by the current carrying by this section. The mmf is distributed linearly because the current carried by this section is how much? I total current. Since it is uniformly distributed, the main current is uniformly distributed, so the main current carried by this section is I x into x by h, Ix by h, and we have assumed that the reluctance of the iron to be 0, or it is infinitely permeable. So the reluctance from this point to this point need to be calculated, and the reluctance is how much? Reluctance is Ws by mu naught into area. Area is how much? Area is Ls into dx. This is the effective area where the flux actually pierces through. It is either like this or it is like this through this element. So what is the flux linked by this element? Total flux from this point to this point minus this point to this point. This we have calculated. We have first calculated phi x, then phi h. Simply integration of d phi x from 0 to x, phi h from 0 to h. Phi h minus phi x is calculated, which is equal to this much. Phi h minus phi x maximum value would be given by just replace I by Im, maximum current, main current. This is the main current. What is Ex max? Ex max is the EMF induced in the element, and it is in quadrature with phi h minus phi x. See, phi h and phi x are in phase because they are formed by the same current, but Ex max is in quadrature with phi h minus phi x. And so what you get is this much, 2 pi f phi h minus phi x maximum. You can see here at x equal to 0, the maximum Ex max is maximum, and x equal to h, Ex max is 0. If I show it on the diagram, Ex max is maximum at the base, Ex max is 0 at the topmost. This can be arrived at from another viewpoint. See, if I choose an element here or here or somewhere here, when I choose it at the element at the bottom, more amount of flux is linked. See, these are the flux lines. More number of flux lines are linked, and if I choose an element here, lesser number of flux lines are linked. So the EMF induced at the base is more, while at the top it is less, and the EMF varies from top to bottom. Since the EMF is not fixed as you change the element position, what we do is we calculate the average value of the Ex max, and the difference between the average value and the Ex max is responsible for the eddy current. So here you calculate the Ex max average. Simply integrate Ex max over the entire height divided by h, which on calculating and simplifying we get Ex max average to be equal to this much, 2h by 3. Now we need to find out at what height Ex max becomes equal to Ex max average. Simply replace h minus x square by h by 2h by 3. Equate it, get the value of x. So Ex max becomes equal to Ex max average at a distance 0.58 h. So in other words, at 0.58 h, Ex max and Ex max average difference becomes 0. If I show it on the diagram, it will look like this. At distance 0.58 h, the difference between Ex max and Ex max average becomes 0, and moving downward or moving up, the difference is negative, and or the difference is difference changes its sign as we move up down. In other words, now this difference is responsible for the eddy current in this element or this element. See here, if I change the distance at distance 0.58 h, the difference between Ex max and Ex max average is 0, so it will drive a zero current at this point at a distance 0.58 h. Now as you move at the extreme end, the difference becomes more, and as you move towards this side, the difference again becomes more, but reverse sign. The sign changes. So we can say that this path and this path will form a loop. This path and this path will form a loop. The eddy currents form loops like this. So here we have calculated Emax difference divided by resistance Rx. Resistance of the element I have already told you, rho ls by bdx. How rho ls by bdx? B into dx is a section, and what is the length of the conductor? Length of the this element is how much? Ls, and area is bdx. Rho ls by bdx. So this is the eddy current. Now what you calculate is eddy loss ratio. Eddy loss ratio is given by eddy current I square loss max by main current I square loss max. We have calculated the eddy current in the element is this much. This on simplifying becomes equal to this much. This divided by the main current in the element square into resistance. Numerator resistance and denominator resistance both are same, so they get cancelled out. So we are left with only I square eddy current divided by I square main current. This is the expression we get, and this is the eddy loss ratio at a distance x. Fine. Now we need to calculate the average value of eddy loss ratio. As I said, this eddy loss ratio is for a distance x, is at a distance x, and it will change its value as we move up and down. To calculate the average value, we need to find the average of this expression. The average of this expression is h square by 3 h square by 3 minus x square whole square h square by 3 minus x square whole square dx, and average over the entire height. We get this value, and then the average value is 4 by 45 h to the power of 4 by the remaining expression. Remaining expression means this entire part. This is the average value of the eddy loss ratio. Now you can see the average value of eddy loss ratio is directly proportional to the square of the cross-sectional area of the conductor. So to reduce the losses, we have to reduce the cross-sectional area of the solid conductor, which is not possible because to maintain a certain ampere rating, we can't reduce the cross-sectional area. Instead, what we will do is we shall subdivide the whole conductor into smaller divisions like this, insulated from each other, so that the total current, same amount of total current may be carried, and at the same time we reduce the losses because B and H are reduced for each individual subdivision. Option 2 is to transpose the conductor. What will happen if you transpose it? Now see, just two conductors placed in a slot, there will be a difference in EMF because they occupy two positions, different positions. This difference in EMF would drive a current which will result in losses. Instead of aligning the conductors like this, we reroute the conductor. We route the conductor like this, so that the difference in EMF between the two are minimum. Let us illustrate with another example. Just observe this conductor. It has 4 subdivisions, 1, 2, 3, 4. So if I look from this side, it will look like this: 1, 2, 3, 4, and at the other end 4 will be at the top, 3 will be next to it, then 2, then 1. So what will happen is the difference between conductor 1 and conductor 4 would be minimum. Similarly, the difference between conductor 2 and conductor 3 would be minimum. So to a greater extent we have eliminated the eddy current loops. To a greater extent we have minimized the losses. And the last thing I want to discuss is regarding the distribution of the total current. Now just look at it. We have already established that the eddy currents are distributed in a manner shown here. They change their orientation as I move both sides from 0.58 h distance. So these eddy currents are in phase with Ex max minus Ex max average, because that difference in EMF divided by the resistance establishes the current. But Ex max minus Ex max average is in quadrature with the flux, and the flux is in proportionate to the main current. In other words, we can say that for each individual element chosen, the eddy current and the main current are in quadrature. If I choose an element at a distance x, the eddy current, let it be written as Ix max, and the main current Ix main. This current would be uniform, but this eddy current would be distributed, the maximum value would change according to this pattern. And when you add them vectorially, what will happen is we'll find that the total distribution of current is more in the outer areas and lesser in the inner regions. In other words, the total current would be distributed larger in the outer areas and would be lesser in the inner areas. This phenomenon is known as skin effect, and this increases with increased frequency. Whenever the frequency, it may happen that the current follows the outer skin at very large outer periphery. Total current is distributed in the outer periphery at very large frequencies, but those large frequencies are not encountered in practice, and we work with supply frequency only. But nevertheless, the current would be distributed in the outer areas. The effective cross section is thus reduced, and the losses are always there due to skin effect. That's all from here. Thanks for watching. Please subscribe.